Okay, I've already demonstrated the Whirley gig apparatus, so what we want to know is what is the mass of this rubber stopper, and I'll draw a little sketch of it. So draw the sketch with me. Here's the PVC pipe, like this. And we've got a little rubber stopper out here, and it's tied to a string, and that string goes into the PVC pipe, and then it's hooked onto a 200-gram hooked mass right here. I'll call this Big M. Big M is 0.200 kilograms. We'll go call this little m. And it is significantly less than 200 grams, because if it was close, this experiment wouldn't work. So, and you can probably figure out why. And so what we're going to do is you're going to whirl this thing around. It's going to woof, 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 like this. And we're going to make certain measurements, and we're going to ask what is the mass of that based on these measurements and calculations. So, first of all, let's this mass right here is just going to hang there, right? It's not accelerating up or down. Once you start slinging this thing around, it'll reach some kind of equilibrium, and it's there. So we can draw a free body diagram of this guy. Now, if I draw a free body diagram of this guy, it's very easy. We have mg, which you can figure out. It's just 0.2 times 9.8. I think that's 1.96 newtons or something like that. And then you have the tension force in the string. So by looking at this guy, we can figure out, oh, the tension force in the string is just equal to the weight in newtons of the mass at the bottom. Does that make sense to everybody? Yeah, finish your text and then look up here. Do you see that here's this mass, it's just hanging there, so gravity's pulling it down, so the tension force has to support that weight. Now we're going to make a simplifying assumption here, and it's almost completely true. We're going to assume that as the string comes up here and through this, that there's almost no friction with the lip of that pipe, and it's pretty close to being zero. I mean, it's not zero, but it's not significant compared to the rest of the forces acting on it. So therefore, the tension force here equals the tension force here. Now I'm going to draw a free body diagram of this mass. Now, in reality, this mass might be a little bit low below here, like this, and I'll show you why. And then it will go around, a little bit below. It's because gravity's pulling it down, right? We've got gravity like this. I'll call that mg. But then we have this tension force like this. And that's the force of the string pulling on it. Now, in my one of the things I do in AP Physics C is we slow this thing down so that this angle is significant. But what we're going to do in here, at least for this first experiment, I am going to give you a problem but anyway, for this experiment, we're going to assume that this angle is very, very small. In other words, it's almost a flat circle. So that means that this angle is small, very, very small. So what that lets us do is this. The radius of this is basically the length here of this hypotenuse is basically the same as this horizontal leg. Because this angle is really small, and the cosine of a really, really small angle is really, really close to 1. And so you just, if this is ft cosine theta, if theta is really small, then cosine of something that's really, angle that's really small is really close to 1, so it's 1 times the tension force, so this is really the tension force. And then the geometry of it, the radius is basically the same as the length of this string. So I'm going through this complicated explanation just to let you know that we're going to assume that this force of gravity is much smaller than the tension force, and it is. And so we're going to ignore the force of gravity on this, for at least for this first problem. So one of the things you have to do is you have to arrange this so you're really slinging that thing around fast, so that it doesn't sink down very much. All right. So that means that I'm going to simplify the free body diagram of this and say the weight is negligible. So really all we've got is this tension force. We're going to turn this into this to make the problem easier to solve. Now this thing is moving in a circle. This rubber stopper is moving in a circle. So therefore, what's true about that tension force? That tension force is a centripetal force. So we can say, oh, okay, the tension force is equal to mv squared over r. Okay?
Is that capital M?
No, this is lowercase m because this is the mass of the rubber stopper now. Because by the way, that's an outstanding question. That's exactly the question you should be asking. Because what mass do you use? You say, okay, what mass is being accelerated? This mass down here, this big one, is not being accelerated. It's this mass that's being accelerated as it goes around in a circle. You have a centripetal acceleration. Okay? So this allows me to solve for the mass. Let's solve this equation for the mass. The mass of the rubber stopper is equal to the tension force times the radius of the circle divided by the speed squared, right? You divide by v squared, you multiply by r, and you get that expression. Now, this expression tells us what we have to do in the experiment. In order to figure out the mass, I need to know what the tension force is. I need to know what the radius is, and I need to know what the speed is. Now let's talk about the radius. This is pretty easy to do. You want to take a meter stick, and I'll go get the meter sticks and hand them out here in a minute. You want to go from the center of the pipe here to the center of the rubber stopper and just measure it like that with the meter stick. Okay, so just measure it. Now, here's something that's a little trick. And I'll hand out tape if you need it. Some of them already have tape on it. You want to be able to measure that radius as it's slinging around. It's really hard to measure the radius while it's slinging around. Someone's going to lose an eye, okay, if you're doing that. So what you do is this. Right here, you put a little flag out of masking tape. You just put some little masking tape right there. And you make sure that you sling this thing around so that the masking tape is barely below the pipe. And then what you do is you have somebody hold this down when it's not moving around in a circle, and just measure the distance from here to here. And that makes measuring the radius really easy. Okay? And it allows you to keep it also allows you to repeat the experiment, right? If you have that little flag on the string, then you just, okay, let's put that flag in the same spot, so then you got the same radius every time. Is that clear? Okay, you'll figure it out. And then, so that'll give us the radius. Now we need the tension force. Well, the tension force is just equal to the weight of this, and it's just 200 grams or 0.2 kilograms times 9.8 newtons per kilogram, and you get the weight from that. So show that calculation. And then you need the speed. Now this is where it's a little bit tricky. This thing is moving around in a circle very, very fast. Well, the speed is equal to distance over time. Well, if you let it go around one time, that's the circumference of a circle, right? If you go the distance it travels is the circumference of a circle. That's 2 pi r. And what is the time it takes to go around once? It's called the period. But here's the deal. It is impossible for you to measure the time it takes to go around once very accurately, because it's going to go swish, 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 swish like that, right? It's going around really quick. So what's the best thing to do?
Guess.
Yeah, guess. That's the best way. No! Grant. All right. No. Let it sling around like that like 20 times and measure 20 of them. Then you'll get a really accurate amount, and then divide by 20. And so the human error is about 0.2 of a second when you're using a stopwatch. But if that 0.2 of a second is divided by 20 complete rotations, you're dividing that 0.2 of a second of error, you're dividing it by 20, and thus the error becomes very, very small. So I would measure the time it takes to go around 20 times. If 20 doesn't work for you, use 30 or 25. I don't care. Just as long as it's clear in your write-up of what you're doing. So now you've already measured the radius. Then measure 20 periods divided by 20, and then you'll have the period. And now you have the velocity in meters per second. Then you take this answer and plug it in here, and then show it really clearly. Really make it clear, what your measurements are. Make a little data table, what your measurements are, what you did, and all that. I'm not going to make you write a procedure for this because I want to get this done during class time. But now you can solve for the mass. And so it'll be blank, and put it in grams. So you'll get it in kilograms, and then just divide it by 1,000 to get it into grams. Then, when you're done, show it to me. And then after you show it to me, then we'll actually measure it with the balance, and then we'll come up with the percent error. I've had people nail this thing, like almost 0% error. I think they got lucky. And then I've had people with about 20% error. Is not that bad considering all the uncertainty in here. But if you get more than 20% error, you probably should do it over again and see, or get help from me. Okay? Okay, so I'm going to hand out the materials and allow you to get started. So for this video, that is all. Thank you. Woo!